All right, so it will be a long presentation, so I think I will be starting now. So this is me, I'm Felix. I'm a PV engineer and software developer at RatedPower, and I joined the company about 6 years ago. And I'm responsible for the energy calculation and topography calculation modules of pvDesign. This is the index for today's presentation. We'll be going over the calculation model itself, the goals of the calculation model. Then we will speak about the 3 core aspects of it, which are the digital elevation model, the installation of structures, and earthworks, and finally a Q&A. So starting with the calculation model itself, first we need to understand what are the goals for this module of pvDesign. Like when looking at the model from a product standpoint, what are we looking at? So we want to model the PV plant topography and generate a PV layout which considers the topography restrictions and which optionally uses earthworks as well. So applying topography restrictions means removing structures, trackers, fixed structures, whatever, because of slopes, and also calculating earthworks when required and when specified by the user. And the calculation model sits in a conjunction of requirements, which are high engineering quality. It has to meet user experience requirements as well, so it needs to be fast, and also programming requirements. Like we want the calculation model to be easy to maintain and reliable. And pvDesign, I don't know if it's visible, but it sits in the middle of those 3 circles, of those 3 requirements. And that makes it harder, of course. Especially the automation aspect of topography modeling in pvDesign makes it very different from other approaches to topography modeling in PV, right? But yeah, this is an explanation of the goals that determine how and why we do things in pvDesign. The calculation model has the 3 components I spoke about earlier, which are the digital elevation model, the installation module, and earthworks. And they are all explained in detail in the topography methodology. You can find it in our knowledge base in the methodologies section. And I recommend, if you're interested into diving deeper, that you download it and read the methodology. The methodology also has all the references, so all the papers and books on which we based the calculations. And finally, this slide showing you the progression and the evolution of the module. As you can see, the first features were released in 2019, but we have been steadily improving it since then, including new digital elevation models and earthworks, etc. So getting started with the digital elevation model. The digital elevation model, it's the core of the topography analysis in the sense that it's how we treat terrain and how we model terrain. The source, the data source for the model, it's a list of points, like you can see on the picture on the right. So points are just X, Y, Z coordinates, right? These usually come in a CSV format or from an API. The digital elevation model will generate a surface based on those points. So we can evaluate random points which aren't in the original data set. And we have some requirements here which are really important, which are that the calculation model can't depend on the structure of the data set. That, in other words, that means that we can't have a dependency on the points being in a grid, for example. It has to be something which can be arbitrary, right? Like contour lines or whatever. And it also has to have high performance, so it needs to be really fast. That's because of a pvDesign user experience requirement. And of course, good accuracy. We want our approximation of terrain to be accurate and to be as close to the reality as possible. So the first digital elevation model that we implemented in pvDesign was inverse distance weighting. This is a very simple calculation involving a weighted average, which I will explain later. And this was the first one we implemented because it was easy to implement and to understand. It was very fast. It has a really good performance. And of course, it doesn't matter what the dataset structure is. So it can be anything from a grid to an arbitrary cloud distribution to contour lines, whatever, it doesn't matter. And that's very important to us because it means that as long as someone uploads a CSV file with the correct format, it will be used and imported correctly. So this feature was originally implemented so that you could upload a CSV file for the terrain and use the slopes analysis tool in pvDesign. That was all that was available in pvDesign at that time. And it was still a very valuable feature. This is diving deeper into how this works. This is a quote I like a lot by Tobler, and he says that all things are related, but nearby things are more related than distant things. And I think that if you keep that in mind, it's very easy to understand what inverse distance weighting is doing. Inverse distance weighting, the calculation itself consists of a weighted average of the elevation of all the points surrounding an unknown value. So in the picture on the right, we have an interrogation, right? And that's the unknown point for which we want to know the elevation. And then we have the sample points, and the sample points are the points in your CSV file, the actual known elevation values, right? And the way to do inverse distance weighting is to calculate the average of the elevation of every point and weighting those values with the inverse of the distance squared. So that's what you see on the right, the W subindex I, 1 divided by the square of the distance. And well, it's easy to relate now this formula with the previous quote that says that all things are related, but nearby things are more important, right? Well, as you can see, because it is the inverse of the square, as things get closer, the distance decreases and the weight increases. And so this is a mathematical representation of that quote, right? It's really cool, I think. And also you see how it's very simple and easy to explain and to understand, right? This is it. Everything else is implementation and coding, right? But IDW interpolation has significant shortcomings, which became apparent after some time. So the shortcomings we observed, initially we called them banding, but later on we learned that they actually have a name, and it's the bullseye effect, which is that inverse distance weighting produces flat surfaces around the known sample points. And this produces a situation where we have like undulations in the terrain, right, which weren't actually there. They were false. They were an artifact of the interpolation rather than a real life thing. So we wanted to find a better interpolation method which produced a more realistic surface, which had higher quality. So the next interpolation method was real basis function. And this was released in the first quarter of 2022. And here the goal was to make a smooth surface based on the same elevation data that we had from Google Earth. And well, as you can see in the picture, we achieved the goal, which was to get a smoother surface. This removed the banding effect, where we had structures which were removed and removed, removed and removed. This didn't happen any longer. And we also obtained like the interpolation was very good performance, so we didn't have a regression in performance. Simulations weren't slower because of this interpolation method. The mathematical explanation behind it, it's way more complicated than inverse distance weighting. A real basis function, it's simply a mathematical function which depends on the distance to something. So there on the upper right, you can see the radial basis function used in pvDesign, which is the square root of the distance squared plus a fixed parameter r. And well, to actually compute the elevation, we need to build a coefficients matrix and solve a traditional matrix problem. The mathematical aspect is very detailed in the topography methodology anyway. So I recommend, if you are interested, that you go look there. Anyway, the RBF interpolation turned out to produce really high quality terrain surfaces with smooth surface, very high accuracy as well, and very good interpolation performance. But it was very hard to implement, in that we spent a lot of time actually getting it right and making sure that it performed well. So this is the default interpolation method for Google Earth data. So this is used for most pvDesign simulations nowadays. So it is an important part of the software. Finally, this was very recent in the first quarter of 2023, we released a new interpolation method for pvDesign, which is the triangular irregular network. This method is only used for custom topography files. And here, so you will recall that earlier on I said that RBF is only used for Google Earth data. That means that for custom topography data, we were still using the old inverse distance weighting method. And that meant that whenever someone uploaded a custom topography file, they were getting a lower quality terrain surface, even though that was the opposite of what they expected, right? Like they wanted to have a high quality terrain representation, but instead it has some issues. Most of the issues actually appeared when people uploaded files coming from contour lines, and terraces would show up in the 3D representation. So triangular irregular network interpolation fixes that. It produces planar surfaces between the known points, and we do this using the Launay triangulation. So initially we construct a grid of triangles connecting all the sample points, and then we interpolate the elevation of unknown points by finding the plane which contains that unknown point and calculating the elevation in that plane. So this is a very well-known interpolation method. It's the one AutoCAD Civil uses, for example. So whenever you import a topography file, a DEM in AutoCAD Civil, it is using this interpolation method in the background. That doesn't mean it's easy. It is a bit hard to get it working right in terms of performance. So it can be slow compared to other methods. But with a bit of work, we were able to get it working. So the advantages of doing the interpolation is that it has a very good representation of high resolution data sets, in that every single hole or particularly abrupt change in terrain is represented correctly. So it retains the maximum level of detail, and that is very desirable. Considering that the use case of this interpolation method is a high resolution topography data, this is a very desirable feature. Another important feature for us, and the reason why we implemented it, is that it processes correctly the XYZ datasets generated using contour lines. It is very often that we find users who have contour lines from a topography analysis that they outsource, and they want to import that into pvDesign. The thing is that doing that is not easy, and one of the things that used to fail was, like I said earlier, the situation where the terrain wasn't realistic because of terraces. So the way to do it is to extract the vertices and upload that as an XYZ dataset in pvDesign, and that still can have problems, right? Like it can be an imperfect solution. However, Team mostly gets it right. There are some shortcomings though that you can see in the pictures on the right. The first is that the terrain surface is discontinuous, in that the slope is discontinuous. So you have these edges whenever we are near a sample, right? A point sample data, and obviously those discontinuities are not real. That's not in the real terrain. Terrain is usually smooth. So that means that, for example, if you are using a dataset with sparse resolution, so say something like 15 or 30 meters, you will have these breaks in the terrain surface which are unnatural. Of course, it doesn't matter as much if the points are much closer. If we have something like 5 meters or 3 meters, then it's really not an issue. But this is something to keep in mind. Another issue is that when you upload a dataset coming from contour lines, whenever there is kind of like a crook in the contour lines, right? Like you see in the pictures, there might appear triangles connecting points of the same line. And when that happens, that means that all the points have the same elevation, and so we get a flat surface in that area of the line, even though that's not really there. And you can see that in the picture on the bottom, where it's very easy to see that in the 3D, where we see terraces in that ridge line. Instead of it being a continuous ridge, it has like small steps, right? So yeah, this happens when you import something coming from contour lines. Of course, it only happens when the contour lines are very complicated. So yeah, in summary, we have radial basis function used by default for the Google Earth data. We have triangular and regular network for custom topography files in CSV format. And finally, inverse distance weighting is still in use today in pvDesign as the elevation model for the overhead line. The overhead line terrain has some particular characteristics which make it unsuitable for RBF or TIM. And so for that reason, we still haven't found a replacement, so we are still using IDW. Finally, it is very important that whenever actually diving deep into topography in pvDesign, you validate the quality of the terrain. And you have several ways to do that. In the first place, you have the Layout 3D. You can download the Layout 3D in AutoCAD format, in DWG, or you can actually also look at it at the web. So without leaving pvDesign itself, there is a tab in the design results which says 3D, and you can see the 3D rendering there. We also have the terrain XYZ document. This is an XYZ file that you can import in, for example, AutoCAD. And it's interesting because it will also contain the earthworks platforms that pvDesign has calculated for you. And finally, a topography analysis in DXF. There you will find the slopes. So with these three documents, you can evaluate terrain quality very effectively within pvDesign. So that is the core of the calculation model, which is how we handle terrain, right? But now we move on to the structures and the PV plant layout itself. And so here the goal is to remove structures in areas of the terrain with high slopes. So imagine we are doing a PV plant design using trackers, and we have a slope restriction in either the north-south or the east-west axis. And we want to make sure that we are not installing structures or trackers in those areas. Here I think there are two approaches to solve this issue. The first is the area-based approach. Here we would find small patches where the slope restriction is exceeded. Those patches might look something like triangles, for example. And whenever we have a structure which overlaps one of those triangles or patches, we remove the structure. So that is something like what you would see on the upper right picture. It shows areas where the slope exceeds 15%, and you will remove the structures in those areas. And then there is a structure-based approach where what you will actually do is you will try to install the structure following the terrain, and then you will validate if the structure meets the requirements or it doesn't. And if it doesn't, you remove it. pvDesign uses the structure-based approach for reasons I will explain in another slide. So the topography analysis feature was released in 2020, and it's a very easy to use feature within pvDesign. You go to design process, and you can enable slope limits in either the north, south, or the east-west direction. And so what happens is that whenever you say the slope limit is 15%, structures are not installed if the slope exceeds that value. You need to enable the remove structures that exceed your limits toggle. I know many people don't understand the reason for that toggle, but there is a good reason to have it. And that is that whenever you are actually using a custom topography file, you may have voids in your data. And if you have structures in those voids, we will remove them regardless of the terrain, because we don't have terrain data. So with the toggle, you can generate a layout with slope restrictions, even if you have voids. So it's a useful feature, and it gives you some flexibility in terms of the analysis that you can do. So moving on, how does pvDesign install the structures? So this is how we follow terrain, and it's a very simple algorithm. First, we locate the position of the piles, and we interpolate the ground elevation in those piles, so below the pile, right? Here, this is why we needed a DEM, why we needed a surface, right? Because we were going to be requiring the elevation of points which weren't initially present in the data set. So these points aren't present in your custom CSV file, right? We need to calculate their elevation in some other way. And that's why we require an interpolation method, a surface, And that is why we have all those different methods. Then, once we have the elevation of the ground in those points, that is step 2, we will perform a linear regression connecting the points. So we will project the points on an XY plane, and then we will perform the linear regression like you see on the right. And it's the exact same linear regression formula that you would use in Microsoft Excel, for example. It's the same thing. And then finally, once we have the regression, we will raise the regression line, and that will form our structure. And we raise it so that we meet a minimum ground clearance requirement. So we look at the shortest pile, and we raise the line so that the minimum ground clearance is respected at that shortest pile. And what this gives us is a structure that follows the terrain naturally, right? Whenever the terrain is flat, the structure will be flat. Whenever the terrain is more or less sloped, it will follow the slope, of course. But what's interesting about it is that if the terrain has holes or other kinds of discontinuities, the structure will try to adapt to that without actually having issues with the hole, right? Like it will try to follow the terrain and average out the hole and find the best adaptation possible to that particular patch of terrain. So then, in order to enforce the restrictions, what we do is that we measure the slopes on the structure itself, so that we will look at the table of the structure and look at the slope of that table and say if the table slope is greater than 15% or whatever value the user has set, we remove the structure. We also look at the length of each pile, right? So because we have calculated each pile individually, we can actually calculate the individual length of the piles. And if we find any pile which is too long, we can also remove the structure using the undulation tolerance filter. And we also look at east-west slopes through looking at the perpendicular lines to the structure. So the advantages of this structure-based approach compared to the area-based one is that in the first place, it is more granular because we are looking at each structure individually. And that allows us to, well, in the first place, like I said, it can smooth over holes or other accidental features which we might otherwise have had as a reason to remove a structure, right? With this approach, we can actually not remove it if the structure can adapt to that feature. It also gives you a strict guarantee that every single structure in the layout has passed your filters and has passed your requirements. So this is very important as well in guaranteeing that your layout is valid. It naturally includes pile length calculation. So this is another thing which we can't take for granted. Initially, you might not have it if you are using an area-based approach, but with this approach, we have it naturally included as part of the calculation. And finally, it allows us to implement some more complicated stuff like undulation tolerance restrictions. It allows us to also look at link trackers in a more detailed way and apply earthworks, which I will explain later. So nowadays, 40% of pvDesign simulations used slope filters, which is, I think it's a very significant proportion. And this is a testament to the success of the feature, let's say, and its importance. And there are very different ways in which you can look at topography in pvDesign, the restrictions themselves. You can apply the filters in design process. Then within design process itself, you can look at the effect of the restrictions because you can recalculate the layout and see how the peak power, for example, changes. So for example, if we make a restriction more strict, so we go from say 15% restriction to 10% restriction, we might expect a drop in peak power because more structures get removed, and that happens. You can see that real time within the software. We believe this is a very powerful tool, right, to do this kind of analysis and to quantify the effects of having different restrictions very easily, right? And when you run the simulation, you have different documents you can use to analyze the simulation, which are the topography analysis, where you have the slopes, but you also have the reasons why each individual structures were removed and the codes for the structure. Then you can go to the listing of posts and you can look up the structure in the Excel file. You can also see the coordinate of each individual pile in this document. As I said earlier, you can iterate within the design process by changing the values. And finally, you have the layout 3D, where you can see the structures as they were installed and the earthworks platforms as well. So finally, earthworks, I'm running out of time here, so I will try to be brief. Earthworks is a very challenging matter for us. It is usually done very manually and based on the experience on the engineer which is doing it. So there is not much literature regarding how to do this actually. So we had to make it along the way, kind of. We wanted something in pvDesign that was very easy to use and very fast as well, and that also made it challenging for us. The calculation model itself has seen 2 releases already. The initial release was in 2021, but it didn't work very well, really. The reason was that it installed individual platforms, and so it underestimated the volume of earthworks that were required for a particular PV plant. The second release made the platforms bigger, and so in doing so, it increased the volume and it made the design more realistic. So yeah, the goal of the model, and this is also something that is very important for us, is that the goal is to produce a cut and fill, so cubic meters estimation, which is within an order of magnitude of the real value. The real value understood as whatever a civil engineer would give you once they run the analysis, right? Here, an order of magnitude might seem like a lot, but we actually think it isn't. And in real life, we think that it actually might be closer to 2 times, either twice as much or half as much, right? But the thing is that it's really, really hard to match the criteria of an engineer who is doing an analysis throughout 2, 3, 4 days, right? While we have to do it in a few seconds based on very few parameters. So that's why we want to give an estimation which comes close, and that's already very hard. Anyway, the model works in the following way. First, we identify all the structures which need earthworks. This is done by finding structures which are within a range of slope values, so say from 15% to 30%. We want to install those structures in whichever way is possible, and we accept doing earthworks to install those structures. So once we have all those structures which require earthworks in order to be installed identified, we group them up. And then we split the groups using a mesh simplification algorithm. And what this algorithm does, and you can see it in the bunny picture, it will try to find surfaces which simplify the terrain and reduce the number of polygons which compose the terrain. And so it's kind of like a first approximation to what an optimal earthworks platform would look like by finding a plane which approaches the terrain very well. And then we do some post-processing of the shapes, both before and after mesh simplification, so that the platforms have reasonable boundaries, which aren't like very irregular or crooked in different ways. This is important to simplify the construction of the PV plant if it ever comes to that. Then regarding that is, and all of that happens in 2D, right? Like the mesh simplification is a 3D algorithm, but the shape algorithms are in 2 dimensions. So once we have the surface that we want to apply earthworks, so we need to compute the actual plane, right, which will be the earthworks platform. To do that, we compute a plane which matches the terrain surface as closely as possible. You can see that in the rotating thing on the right. And then we rectify the slope of the plane by matching the slopes which are the restriction of the structure. So imagine that the structure has a restriction of 15% in the north-south axis. Well, I mean, it wouldn't make sense to install an earthworks platform which exceeds the 15% slope value, right? Like we want to be able to install those structures. If the slope is greater than 15%, that is impossible. And that can happen if the terrain is very slopey, right? So we need to change the slope of the plane by turning it around an axis. Then we move the plane up and down so we can balance cut and fill. Right now, pvDesign will find a perfect balance, a 50% cut, 50% fill balance. And finally, we reinstall the structures on that plane, and that gives us the final result. And then, of course, to calculate the cut and fill volume, we compute the elevation difference to the ground, and we multiply by an area. So it's like we do a small squares, right? And we compute that column of terrain either above or below ground, and we apply, and depending if it's positive or negative, it's cut or fill. Nowadays, 26% of pvDesign simulations are using earthworks, which again, it's a very significant proportion. And it's very easy to use. You use it in the same design process tab as the regular topography filters, and you specify the slope range where you would like to apply earthworks. And when you apply earthworks, you will usually get an increase in peak power because you are installing more structures. Of course, this is a trade-off. You get more peak power, but the plant is harder and more costly to build, so your capex goes up, in other words. And finally, you can review the earthwork solution in several documents. You have the bill of quantities to see the cut and fill volumes. The listing of posts has the list of platforms. You have the layout 3D, where you can actually see the platform design in 3D and rotate around, zoom in, all of that. And you can also see the platform boundaries in the topography analysis in the XF in 2D. So with all of those documents, you can actually have a very detailed look at the earthworks. Oh, and I also forgot to add it here, but in the terrain XYZ documents, you have the final terrain surface with the earthworks platforms. So the terrain actually calculated by pvDesign. So with that, this is the end of this presentation. And so yeah, please, if you have any questions, you can use the GoToWebinar chat and ask any questions. We have about 10 minutes until the presentation ends. So let me see. Okay, here are the questions. So sorry, I couldn't find them. Right. So first, the first question is, what are two of the best sources for topography information when using the pvDesign app for providing consulting and engineering assistance to a client? I would say the best topography source is any kind of custom topography you can find, either in a public database, like in the US, you have the USGS. Here in Spain, we have the IGN, Instituto Geográfico Nacional. Those are very good sources for preliminary design. Other than that, any custom topography, like if you can get a topographical study of the terrain, that's perfect. Second question, how reliable or accurate is Google Earth in providing topo data? The answer is, I wouldn't say it's reliable at first. So the thing is that we don't really know what data set Google Earth is using in the background. They are not transparent about that. So the base data set is a STRM-30. That's Shuttle Topography Radar Mission. It's a data set from the 90s, and it has a 30 by 30 meters resolution. That's the base. It can be better than that in some locations. But the thing is that we don't know when it's better. So we can't actually tell. Google Earth data, in my opinion, is useful for the preliminary design stage. It's useful because you get it by default without any effort. You upload a site in pvDesign and you automatically have it. And it's very good to notice if there are significant issues with terrain or not. So if you have a significant slope, like a large area with a slope greater than any restriction, it will show that. But it won't show if you have holes or other kinds of accidents in the terrain that won't be present. So it's very good as an initial analysis, but if you want to dive deeper, you need to get better topography data from somewhere else. Also, I would say that it's good to realize if you're going to have issues. If the terrain is complicated, it will show in the Google Earth data. If the Google Earth data is flat or very simple, it's probably going to be fine. So yeah, it's a very good initial estimation, let's say. And finally, can an EPC rely entirely on pvDesign generated data for structures, sizes, and placement, or do airline surveyors need to do also their own topography prior to installation? I would say they need to do their own topography prior to installation, for sure. pvDesign, it's a very good preliminary analysis tool. And with high quality topography data, and if you review the position of the piles, it's a very good approximation of the position of the structures. But the thing is that the structure manufacturer isn't in the loop, right? So any particularities of the structure model that you have, pvDesign might not be taking that into account. So I'd say pvDesign is very good for your initial analysis. It's very good for getting a quote, a very, very, very in-depth quote, very easily, very quickly. But detailed engineering, that's something you always need to have someone, an expert looking into it, right? So yeah, that would be my answer to that question. Moving on. Will we receive a link with a review? Yeah, apparently yes. Then, how to deal with slopes erosion over the life of the asset? Let's see, I can't read the entire question. Let me see. Right. To be honest, I don't know. In RatedPower, we focus in the preliminary stage, preliminary design. So I wouldn't know how to deal with this. I'm sorry. Is your earthworks analysis automatic, or do you need to look at the site area by area? No, it is fully automatic. pvDesign does it all on its own. All you need to do is either, well, you can use the Google Earth data, or you can upload your own topography data. And then you need to set the limits. So you need to set the topography restriction values. So the up to 30%, and that's it. You get the full earthworks calculation and platforms. How high is the spatial resolution that Google offers without using its own data? Well, I said I was answering this earlier. The base resolution for Google Earth data is 30 by 30 meters, but it can be better in some places. Like I've seen information online saying that in some cities, for example, Google Earth has actually LiDAR data, which seems kind of crazy, but that seems to be the case. I've seen some PV plants in Europe using pvDesign, using Google Earth data, which seem to have very good resolution. So I think that it's very probable that in many places in Europe and in the US, the resolution is much better than 30 by 30. But like I said, the issue is that we can't tell. The Google Earth isn't transparent about what is their data source at all. So we just don't know. Which means that I think you need to look at the terrain yourself and evaluate the quality on your own, if you are interested, right? The other solution is when you are doing a detailed topography analysis, find your own data which you are confident in, right? Something like what I said, USGS, IGN in Spain, or whatever. Might this affect dragging structures? I don't know what this question is referring to, but dragging structures are considered and they are installed following the terrain as well. So yeah, those are the questions we have right now. Are there any more questions? I'll give you a minute to drop in other questions, and if not, we will end here. Oh, we have another question. Is there a continuing evolution of the current topography modules? Yes. Right now in the roadmap, we have a new feature for topography, which is going to start development in the next quarter. That's Q3, which is the possibility of defining positive and negative slope values in either direction. So that means you can define separately the limit in the north positive direction and south negative direction. So say you want to be more restrictive in slopes looking north, you will be able to do that. That is a major shortcoming out of the current implementation that we want to fix, and we will be fixing that issue very soon. Other than that, we don't have anything in the roadmap. We plan to continue improving the earthworks feature at some point in the future, but there isn't anything planned, and we are really kind of in a receiving feedback stage regarding that. So if you have anything you want us to develop, and if there is any feature you really need, please make sure to email us at the customer success team, and we will be looking into that. We actually have more questions right now. Is there an extra cost for terrain analysis? No, this is included in your base pvDesign license as everything else. Is your software comparable to PVKs? Excellent question. PVKs, so it's meant for a different kind of analysis. We are in the preliminary design analysis. I think PVKs is more geared towards the engineering detailed analysis. And it's also harder to use. It's an AutoCAD plugin, so you need to have someone who knows how to use AutoCAD and to get that kind of workflow going, right? And pvDesign is more meant as something which is very easy to use and gives you a lot of information with very little effort. Of course, because pvDesign runs on AutoCAD, you can get much more detailed and customized analysis using that, and a more customized PV plan design than you can with pvDesign. So yeah, pvDesign would be your first tool to look at topography, and then moving forward, you might at some point be using PVKs or not. Finally, do you have a need for high accuracy LiDAR topos within your platform ready to order? Not right now. We do not provide that. So if you have LiDAR information, you can upload that into pvDesign, but we don't have that need within pvDesign to actually give you that information automatically. So yeah, LiDAR is something our customers would buy on their own and then upload that information into pvDesign. So yeah, that's it for this presentation. We are out of time. So thank you so much for attending. Thank you very much for your questions, and have a nice day.